Just the
But
power saving alone could justify using that quantum computer.
see, I never thought of it that way because I always think of a computer by itself. Right, 256 qubits doesn't sound very big,
Well,
right?
256 qubits, 2 to the power of
Two to the power of
256 is a
256.
huge number.
It's a huge number. Welcome to Embracing Digital Transformation, where we investigate effective change leveraging people, process, and technology. This is Darren Pulsford, Chief Solution Architect, author, and most importantly, your host. On today's episode, Practical Quantum Computing, part 2 of my conversation with Yuval Boger, Chief Commercial Officer at QERA. Okay, so I think we scoped this thing out. I know what a quantum computer can do. I got to learn how to program one because it sounds super cool. Hopefully, it's easier than doing assembly language. I got to look into some of those software kits because I programmed assembly language in college. Never had to do it. Well, all right, I did a little bit here and there for driver stuff, but that's not fun. That's not fun stuff, right? It's tough. But let's talk about some of the challenges of quantum computing, because we've seen a couple breakthroughs, but I haven't heard the proverbial I can buy it for my home. Because right now, if I remember right, it takes basically an energy source that's massive. I can only run this near absolute zero, right? I mean, it takes a lot to get these quantum computers to behave. Um, so are we seeing any changes in that? Because that's what I just read in the press.
So let's break this down. Um, First, you can use quantum computers today. Many quantum computers, including QERA's quantum computers, are available on the cloud, meaning whether you use Amazon AWS, what's called the quantum services called Amazon Bracket, or use Microsoft Azure, or use Google Cloud, several quantum computers are available there. So if you have a credit card, you can, for a few dollars, run your first quantum program, and very often for free. So
Oh,
there's no
that's
need.
cool.
And so you may not need that in your home because you can use it over the internet, just like you may not need a supercomputer in your home today because it's available someplace and does what
Right.
it needs to do. Now, of course, if quantum computers were easy, then everyone would do it. And so part of the fun is that it's difficult. And, QERA is based in Boston. It's the outgrowth of some world-class labs from MIT and Harvard. Um, they barely let me in the company. I only have a master's in physics, not a PhD, and not from Harvard. So I had to sort of weasel my
Yeah.
way in the door.
Who do you have pictures of there, Yuval? I mean,
I
how
know.
can you get into that club? That's awesome.
Well, but these qubits, these quantum bits, there are many different ways of creating them. And
Okay.
so a lot of the discussion around the world is what is the best way to create a qubit. So some companies like, say, IBM, believe in what's called superconducting qubits. In superconducting qubits, you take special material and you cool it, as you mentioned, to near absolute zero, and then the magic happens. At QERA, we use a technology that's called neutral atoms. In our case, every qubit is a single atom. It's just an atom.
Whoa.
It's an atom. In our case, it's a rubidium atom. Rubidium is on the left side of the periodic table, a few rows below hydrogen. And each of these rubidium atoms, I know this is going to sound science fiction, but it is true. Each of these rubidium atoms in our computer is held in place by a tiny laser beam, one beam per atom. And then when these beams move, the atoms move with them. So if I have two beams, I can sort of get the atoms closer or farther. When the atoms are far apart, they don't care about each other. When the atoms are nearby, you can get them to interact with additional laser beams or additional electromagnetic fields. So when we have a computer on Amazon Bracket, as we described, we have a 256 qubit computer, meaning that you could basically tell that computer take 256 atoms, put them in nearly arbitrary position, get them to interact with each other, and then measure the result. The advantage of our approach is that it does not require cryogenic cooling. It actually works at room temperature,
Wow.
which is really cool. It's really nice if you want to integrate it into, well, maybe not your home, but into a data center. And you say, I don't need nitrogen, I don't need helium, I don't need any special. I just need air conditioning. I can put it at a normal data center temperature, and as long as you have temperature stability, then you're good. You mentioned briefly power consumption, and actually that is a huge advantage of quantum computers. When you look at today's most powerful classical supercomputers, they take megawatts and megawatts of power.
Yeah, they do.
You
Yeah.
need essentially a little power, or not so little power plant next to where the computer is there. Our quantum computer, 256 qubits, takes about 7 kilowatts of power. 7 kilowatts, if I'm lucky, I could find in your living room. It's like 3 hair dryers operating at the same time. Now imagine if a quantum computer could solve with 7 kilowatts, or maybe next generation 10 kilowatts, right? If a quantum computer could solve with 10 kilowatts a problem that a classical computer solves with megawatts, just the power saving alone could justify using that quantum computer.
See, I never thought of it that way because I always think of a computer by itself, right? 256 qubits doesn't sound very big,
Well,
right?
256 qubits, 2 to the power of
2 to the power of
256 is a
256.
huge number.
It's a huge number, right? Because I'm looking for, because we're used to megabits, right? This is not even a kilobit or a
And
kiloqubit, a kiloqubit.
right,
So we're so used to adding, 1,000 onto. Hey, I have a petabyte drive. Ooh, a petabyte drive. Wow. Well, and guess what? It used to be a terabyte drive was huge, right? So with this, we just have to think that it doesn't scale linearly. It's scaling exponentially on what it can solve, the number of superpositions that it can be in at the same time. All right, folks, a quick breather here. In my time of working with tech company founders, I come to one important realization. Certain tools can truly be a game changer. That's why I'm excited to talk to you about Nasuni, an enterprise data platform for hybrid cloud environments that powers business growth with effortless scalability, built-in security, and fast edge performance. Nasuni consolidates network storage and backup, eliminating data silos without changing your apps or workflows. Clients love the easy setup, rapid file sharing between offices, and the ability to leverage detailed analytics that matter. Data fluidity from the unique way data is stored increases its value, providing support for future AI initiatives. Plus, the centralized management model frees up your IT team to focus on more strategic business objectives. Head to nasuni.com/embrace to see how it can revolutionize your data infrastructure today. All right, now back to the show.
absolutely. And let me give you another frame of reference. So when people started building quantum computers, they wanted to build simulators. Say, okay, well, can I simulate on a classical computer what a quantum
Yeah,
computer does?
Intel actually has that. Yeah.
Yeah, it helps me sort of learn how to program. If I want to write a program with 10 qubits, I don't need a quantum computer. I could just have a simulator. Well, the world's largest, fastest, meanest, baddest supercomputer can simulate about 50 qubits, maybe 53, maybe 55. We have a 256 qubit computer. There's no way it could ever be simulated if we use all the qubits and if they're all interconnected and tangled with each other. Then you just cannot simulate it classically. And that just gives you a sense of the power of even existing quantum computers.
So this is really you broke down a lot of the myths around quantum computing. I can have access to it today. You said it's on AWS bracket, right? So I can, and there's programming languages out there today that I can start using. There's programming kits. I know Intel has one. I'm sure you guys have some as well. Um, so what's stopping? Why isn't it like Gen AI? Why hasn't it just exploded?
Well, Gen AI, we like to say, is an overnight revolution that's 30 years in the making.
There you go. You're right. It is 30 years in the making, but there was some incident that happened that just made it explode
Exactly. And so a lot of people are asking, well, what's the chat GPT moment for quantum?
for quantum. Yeah.
And so a while ago, a few years ago, Google published this, what they called quantum supremacy experiment, where they said, we found a problem. It's not useful to anyone, but it's there, that we could prove that we could solve on a quantum computer much, and a classical computer would never do it. So that's nice. It's progress. It generated headlines, helped with everyone funding, helped create the excitement. But imagine I go back to traveling salesperson. If you could show that you can actually solve true business problems, that would be a chat GPT moment. And by the way, the chat GPT moment for material science and pharmaceuticals may be at a different time scale than one for optimization or one for machine learning. So I think it's all coming together. But what's stopping quantum computers today? So there are two things that are stopping them, or that are the reason that we're not there yet.
Okay.
One is the scale. So how many qubits do you need? We spoke about Shor's algorithms. Well, you need more qubits than are available today to run Shor's algorithm. I guess that's good news, because otherwise I could break
Well,
into.
unless China or the U.S. government has one that has 2,000 2,000 qubits, then they can hack every RSA encrypted algorithm out there. It'd be done like that, right?
Well,
And if you had one, would you tell anyone? I wouldn't
if
tell
I
anyone
tell
if I
if I tell if I tell you, I'll have to kill you, right? So
Yeah, that's right.
I'm not
Yeah,
telling you, right?
exactly.
But so
So okay, so
size.
I see that.
So
Yeah.
scale is one topic, and scale is actually, we spoke about different modalities, different way to build qubits, superconducting. In our case, neutral atoms, and some people have what's called trapped ions. Some use photonics. So, and every technology has its advantages and disadvantages. So, for instance, for neutral atoms, because these qubits are individual atoms, we believe we can put 10,000 qubits, 10,000 atoms on a single machine,
Yeah.
and so you have a really powerful computer. But the second thing, these qubits, regardless of how you make them, are fragile. They're fragile in the sense that they're sensitive to temperature changes, to cosmic rays, to mechanical vibrations, to imperfections in the lasers or whatever, or the control signals that drive them. So, a quantum computer today, if you run a sufficiently long calculation, develops errors. And if if it's long enough, then the data is essentially
It's
useless.
useless. Yeah.
So there's a big effort worldwide, and Quera is fortunately one of the leaders in that, in developing what's called quantum error correction. So quantum error correction is, how do I make computers, how can I detect and correct errors for them? And so for that, what's oftenly used, in the term that's oftenly used, is what's called a logical qubit. A logical qubit is a collection of several, or sometimes many, physical qubits that together can detect and correct errors. So let me give you an example, sort of a classical examples. Let's assume you and I were talking, and I was outside and the wind was blowing, and so you couldn't hear me all that well on the phone. And I wanted to give you my credit card number. Uh, and so, but it's noisy. So what I would do is, let's assume that my credit card number starts with 4 5. I would say, maybe I would repeat every digit multiple times. I would say 4 4 4 5 5 5. Or if it's really windy, maybe I would say 4 19 times and then 5 19 times, assuming
Gotcha.
that you could figure it out. Say,
Eventually
oh,
do it.
I
Yeah.
think I've heard enough times 4 and enough times 5 to do that. So that's what a logical qubit does. It takes the information from a single qubit and kind of spreads it out across multiple qubits. And then there's some sophisticated logic to be able to detect and correct. And so if
Got
you
it.
have these logical qubits, then the assumption, and we've demonstrated that in breakthrough research late last year, that yes, you could get better error rates. You can make computers that are more resistant to these
Quantum
environmental
error.
changes. And so if you can get a lot of qubits and you could get error correction in place, then you've hit nirvana. Then you really can do things that
Then you,
can really fulfill the promise of quantum computers.
so the fundamentals aren't quite there yet. We're getting close.
We're getting very
Um,
close.
and there's plenty of problems for them to solve. The next thing would be ease of use and accessibility. Accessibility on the cloud, that's very good. What if I don't trust my data in the cloud? Do you ever see them getting small enough and not as fragile, I guess is the right word, where I can have them on a phone, I can have them, in my data center in my own company or at home? Do you
Sure,
ever see it moving in that direction? Or
absolutely.
will
So,
this always be like a supercomputer?
well, if we think of the classical analogy, the phone that you have in your pocket would have definitely been considered a
A
supercomputer
supercomputer. Yeah, you're right.
some
Yeah,
years
you're
ago.
right. That's
But
true.
but but we certainly do see the need, and we have customers that are buying computers for what's called on-premises installation in the data center. We've announced 2 deals this year. One to sell a computer to AIST, which is the National Institute of Standards in Japan, and another to sell as part of the UK National Quantum Program. And you could say, well, why do people want to have quantum computers on premises as opposed to on the cloud? Could be a couple of reasons. One reason is control. I want to know who's running and what priorities they're running. We just did a survey of almost 1,000 people, and we asked them, do you ever worry that quantum is going to be like AI, where you just cannot rent enough GPUs on the cloud?
Yeah, yeah, yeah.
And say, oh, yeah, that's a really good point. I should really have my own capacity, because if these computers are truly useful, I don't want to have to fight with everyone else on using them. Sometimes, of course, whether it's a pharma company or a
They don't want
defense
that data in
institution,
the cloud
they just
anyway.
don't
Yeah,
want the data in the cloud. They want it
yeah.
there. The and uh, the third reason is because quantum computers cannot run very, very long algorithms. And because quantum computers are not perfect for everything, not for visualization, not for data processing, not for reading from a disk drive, then a lot of algorithms are what's called hybrid algorithms. They combine classical steps and quantum steps. And sometimes they sort of ping pong between each other. And when you place the classical computer next to the quantum computer, you can reduce latency. You can have
Yeah.
sort of these really quick interplays. And last, we spoke about sort of how a lot of nations are both excited and frightened at the prospects of quantum computing and want to make sure that they have this capability in-house. Those nations that missed on AI or missed on the internet
Yeah,
or
yeah,
missed
they got to
on
get in front
5G.
of something, right?
And so today, last time I looked, there are 41 national quantum programs where
Wow.
41 nations are investing sometimes billions of dollars in creating their own quantum economy. And so you can imagine that a certain, pick a country that's not a US, maybe they want their computer in country. They don't want the computer in Boston, Massachusetts.
No, they
They
don't.
want it
Yeah.
in Finland, or they want it in Singapore, or they want it in Japan. And so that's yet another reason where people are buying these quantum computers, even though we still have ways to go before they're truly useful and truly solve substantial business problems.
It's really interesting because hearing you talk, and you've mentioned it several times, the future is hybrid. The future is classical, quantum, and machine, and we're starting to see the emergence of NPUs, for example. So the computing ecosystem is becoming more complex, not simpler. So this is going to require really good programmers, really good systems architects. It's going to require a lot more thought behind the way we architect our infrastructure to handle multiple types of solutions.
Absolutely.
So it's exciting. It is very exciting.
It is exciting, and we work today with a lot of HPC, high performance computing center managers to say, what does this mean? How does this integrate? Do I need
Right.
cryogenic cooling? Oh, I don't. Great. Do I need any special energy? Oh, no. Great. Okay. How does it work? How do I program it? Can you help me? How do I make this available to my users? How do I train a bunch of people to maybe my users they're chemists or geologists or they don't
Yeah,
know quantum. They just
they
want to
don't know
solve
quantum
a problem.
computing. Well, software engineers don't even know how to program a quantum computer yet, right? It's so new. It's a very exciting field. If people want to find out more, um, than just listening to this awesome podcast that we're on, where do they go to find out more about quantum and become educated on what it is, how to use it, and maybe even learn how to program it? Where do they go to find that kind of information?
So if they want to learn about neutral atom technologies and a lot of the terms that we mentioned on this podcast, they can definitely go to quera.com, quuera.com. Yours is an awesome podcast. I also dabble in
Thanks.
podcasting. I have a podcast called the Superposition Guys podcast. I published by now more than 100 episodes, and they
Oh,
feature
great. Oh, awesome.
all kinds of quantum leaders, whether they're providers of quantum or end users or book authors and so on. So it also is an interesting place to look. One of the wonderful things about the quantum industry is that it's an open industry right now. People are mostly collaborating with each other. It's not the car industry where if Toyota sells one more car, then maybe Ford sells one fewer car. We understand we can grow the pie together. And so there's a lot of open exchange of ideas. There's a lot of educational material, a lot of online courses to learn quantum, to dabble in quantum programming. So please join us. It's not just for PhD physicists, it's for programmers, it's for people who want to build, to assemble, to service quantum computers. It's an emerging industry, and it will be a very big thing in the next few years.
It's really exciting. It reminds me of what was going on at the turn of the millennium with grid computing, if you remember that. Yeah, and you were around for that. You're gray hair like me, Yuval.
I,
Um,
I am.
so I was part of the Global Grid Forum at the time. So there was a lot of energy, a lot of sharing. It was a fun time, and it sounds like quantum computing and the community is in the same space. So that's wonderful. Uh, Yuval, thank you for coming on the show. This has been wonderful. I appreciate the time, and I look forward to seeing where this goes. It's going to be a fun, interesting technology as we watch it grow.
It is fun. And Darren, thank you so much for having me on the show.
Thank you for listening to Embracing Digital Transformation today. If you enjoyed our podcast, give it 5 stars on your favorite podcasting site or YouTube channel. You can find out more information about Embracing Digital Transformation at embracingdigital.org. Until next time, go out and embrace the digital revolution.